The equipment and ingredients you're going to need for this episode include an empty can,
a large bowl,
a set of tongs,
some water,
and a stovetop. The first step in our experiment is to take some cold water and fill up our bowl.
The second step of our experiment is to pour about 100 milliliters of water into the can. Turn your stove to medium-high heat and place your can with the water in it in the center of the burner. Leave it there until you see water vapor coming out of the top. Now quickly dunk your can into the water.
Let's look at this experiment a little closer. Before we heat our can, it's filled with liquid water and gaseous air molecules. Heating our can adds energy to our liquid water. The more energy we give our water molecules, the more excited they get, and the further apart the molecules spread. Once enough energy has been added to our liquid water, it changes state from a liquid to a gas. This gas is called water vapor. As our water vapor fills our can, it presses against the sides of our can, creating an increase in pressure. When we place our hot can upside down in our cold water, all the water vapor molecules that fill our can get really close together and turn into a few drops of liquid water. This liquid takes up a lot less space than a gas. Water in its liquid state doesn't exert nearly as much pressure on the inside of the can as it did in its gaseous state. At this point in our experiment, the outside atmospheric pressure is much higher than the pressure inside the can. In nature, pressures want to be balanced or in equilibrium. This imbalance causes the can to violently collapse, creating a balance between the pressure inside and outside of the can. This violent collapse toward the center of the can is called an implosion.
The next example, which would be you have a fixed pressure, because this is basically right at atmospheric pressure, and you change the temperature drastically, you can get the volume of this to change. Now, normally you see this done with liquid nitrogen or waiting a really long time to put it in the freezer, but I have a funner one. As you may know already that I am a fan of canned air because it's actually not air, it's difluoroethane, which was very useful in my previous experiments, but it's also very cold. And it says right here to hold can upright and pull trigger to clear valve of liquid. Now, of course, I'm going to break the rules, which is not safe. So I'm going to hold it upside down and squeeze it this way. And you'll notice that you see a mist that comes out. Now, that is a super cool liquid, and if you get it on your hands or on your face, it can cause frostbite immediately, and so you should treat it with a lot of caution. But if you want to do something to, say, cool down this balloon really quickly by changing the temperature drastically, all you have to do is spray it on the balloon. The balloon will cool down very rapidly. And as you can see, it's shrinking. So this is as the temperature changes, the volume also changes. And if we go ahead and warm it up real quick, the balloon turns to, again, back to its normal size. Now, the next thing that you might notice is when you are spraying from this canister, or any other canister like hairspray or cleaning fluid, if you go ahead and hold the trigger down long enough and just hold on to the sides of the container, you'll notice that it gets suddenly very cold. So what's actually going on here is the pressure inside the fixed container is going down. So what you do is you change the pressure and you get a temperature that goes down. If the pressure goes down, the temperature also has to go down. Word to the wise about using this particular brand in the way that I just have. Aside from it being somewhat dangerous, they also included a bitterant so that people don't huff this to get high, which obviously wasn't what I was after, but apparently I got a little bit too close to that balloon and got a really good whiff because, man, does my mouth taste horrible. And you can't brush it out, and it just lingers in the back of your mouth and it makes you gag. It's really horrible. I've got my...
We need to talk about temperature and pressure. I just got a liquid crystal thermometer from a pet store, it's a fish aquarium thermometer. I've taped it to the end of the fizz keeper. What we're going to do here is look at the temperature. And the temperature, sometimes there's two different temperatures showing a color. I tell them to pick a color. In this case, that kind of brown color is showing at the 78 degrees Fahrenheit. I say stick with that one. And I'm going to speed through this and show that as they pump this up, the temperature will rise. I like this better than a typical glass laboratory thermometer. There we go, we're into the brown is into the 82 now. And we can keep going with this. What we're doing is we're increasing pressure inside the bottle, and the temperature is going up. Now, so I'll show you what happens, and then we'll try to figure this out together. Another fizz keeper, it's full of water. The eyedropper is mostly full of air. The ketchup packet is the way it came from the store. And you got to play around for ketchup packets because some of them don't float. But this one does. And I make sure it's screwed on tight. And I pump the bottle, and what I want them to see is what's happening inside the eyedropper. And if they can see it, what's happening to the ketchup packet. That's not always so visible. So let's focus on the eyedropper first. Yep, that ketchup packet wants to be in the way. The eyedropper is filling with water. Does that mean the air is coming out of the eyedropper? Well, no. If the air were coming out of the eyedropper, we'd see bubbles. And we don't see bubbles. So what's happening to the air inside the eyedropper? It's being compressed. All the air that was in there to begin with is still in there because we didn't see any bubbles. But it's taking up less volume. Okay, so we're doing a pressure-volume relationship. Also, since the eyedropper is filling with water, the eyedropper is becoming heavier and therefore more dense. So we should be able to get that eyedropper to sink all the way to the bottom. Well, now wait a minute. The ketchup packet is also sinking. Why would the ketchup packet sink? I'm not pumping water into the ketchup packet, so I'm not increasing the mass of the ketchup packet. I must be changing the other thing that affects density, which would be volume. You're increasing the pressure, which will be compressing that air, causing the ketchup packet to take up less volume. The eyedropper is more mass, that's why it's sinking. The ketchup packet is less volume, but the same mass, and that's why it's sinking. We're going to start with seeing how temperature affects volume. So we've got a Mylar balloon up front, and if we can get a close-up on the back of this balloon, what I did was I took a little drinking straw and I cut it small and I taped it to the back of the balloon, and that serves as a holder for this string, which I don't know if you can see or not. It's just fishing line, taped, anchored at the bottom, and it's also anchored at the top so that it's taut. This is my guide wire, and the balloon is free to go up and down. When I went to the store to buy the balloon, I asked for them not to fill it all the way because I want some room for expansion. And as I was checking out, the woman said, well, they can fill that up for you. I said, no, this is the way I want it. And in fact, I may let some more air out or some more helium out. But it is filled with helium. And at the bottom, I have paper clips, and it's trial and error. How many paper clips do you need to get the balloon to stay down but be able to rise as well? You can help it along. This is just a heat gun. It's a paint stripping gun. Okay? It's like a hairdryer, except it doesn't blow as much air and it gets hotter. And so what I'm going to do is heat the balloon. Now what I want them to focus on, and what the questions lead them to without being too blatant, is what they're looking for is that the volume is going to increase. So right here I've got a section of balloon that I've intentionally collapsed a little extra. So we're going to look at that section of the balloon as I heat it. And we should be able to see that as I heat the balloon, the air inside is going to increase in temperature, and that collapsed section of the balloon is going to fill. And as that fills, we've increased the volume without increasing the mass, and therefore the density should decrease. And it should rise on its own. As it shrinks, the volume changes without the mass changing, and therefore the density decreases.